Okay, exactly. Exactly what you're talking about is something really problem today. Yeah, exactly. This is this e by square root of this square root of e 2e by 2 square root of eb by 2. Okay, so 2e by 2 into cos of 2 pc 2 fect into 2 of these things, and phi is 2i minus 5 by 4, 0 less than or equal to less than, otherwise value. This is the exact equation of this. Okay, now, okay, exactly, right. Okay, this is the absolute equation. So this is the equation is given by. Now, because once is signal, that means whatever the BPSK, okay, exactly, the BPSK, right? The BPSK as the given equation of the 2 by this signal space diagram of the QPSK is as exactly shown here. QPSK, because look back, QPSK has the equation of the 2 equation cos 2 pi ct into sin 2 pi ct, exactly cos 2 pi ct and sin 2 pi ct, that is a QPSK. Okay, so here the 2i minus 1 pi by 4, this is exactly the equation expanding the square. Okay, right. When you expand this equation comes, look back here, one of these absolute with the cos 2 pi ct into to square root of 2 by t into sine of 2i minus pi by 4. Here this sine I by t integral square root of eb. This is the original BPSK. When you compare this QPSK and CPSK, we look back here, this is exactly one equation. Another equations here, that means there are the two phases, that is cos 2 pi ct and exactly the cos 2 pi ct and the sin 2 pi ct. Okay, exactly, right. Right, so this is absolute. Okay, exactly, pi 1 of 2 2. See, this is when you say this, as you know, the energy of the signal is equal to consist of energy of the signal into what exactly, cos 2 pi ct, that is phase basis function of this and basis function of this. So the basis function of this is equal to this much. Okay, exactly, so that means absolutely is given. Okay, right, absolutely this is the value. All right, uh, right. So this is comparing the comparing with this, the basis phase of this basis phase of the functions is like this. Okay, when you compare this, I'll get back to this. So quadrature, look back here, see one symbol in a QPSK, I'm going to send one QPSK one. What will happen is exactly one for a one symbol, let us say 1 and 0, you are going to send 2 bits 0 and 1. You're going to send 0 and 1 of that. That means for one signal we are going to send a 2 signals. Okay, exactly here. Once, okay, exactly 1 1 0 1 0 0 1 0 pi by 4 3 by 4 5 by 4 7 by 4 plus plus minus minus plus minus minus plus minus signal characteristics. This is what exactly, please mind it. Here we are going to send with the frequency plus 1 1 0 1 or 0 0. That means, for example, if I want to transfer the bit 1, we'll have a bit, that is a symbol, we have a bit 0 0, we are going to send it 2 bits. That means for one signal, we are going to send it 2 bits absolutely with this values, which is, this is exactly, as you know, the signal space is most important. From the signal space, receiver will conclude whether the signal is, will be fall within the range, within the region, and hence exactly what will happen, we'll able to get minus 0, 1, 1, 1. This is exactly the message point. Okay, right? So this is the QPSK form I told you. For a one input, we need a 2 symbol. For example, let us say this is a symbol you would need to type 0, 1, 0, 0, 1, 0. So how the things will go? First, it will take the odd, and next will take the what exactly? Even. First, it will take the odd. The second exactly will take the even. Then absolutely odd and even will be multiplied. Odd and even will be added together, and we can generate a 2 QPSK. Look back. Add is absolutely a in-phase path, and even is equal to what? A quadrature path. Okay, exactly. That is exactly, I mentioned it already. How the generation of these two goes? Generation of the QPSK. This is the signal. Let us say signal is equal to 11001. The binary. This is absolute. The binary, the binary. Okay, binary pulses of the polar will absolutely within this. This is the binary input signals. We'll put it across the what? Binar polary. Okay, and this will be multiplied with what exactly? Demultiplexer multiplied. That means what will happen? This will identify the, okay, this will absolutely, this will be demultiplex. That means the signal will be changed into what? 5, 1 or 2 signals. Okay, exactly here. This 2 signal of the, look back here, that is S1 or T. Then it will be multiplied, as I told you, that whenever the signal to be transmitted, it has to be multiplied with what exactly? The basis functions. Okay, exactly. The basis functions. This has multiplied with the basis function of this, and we will get back to 2 symbols. S1 of 2, S2 of 2 is equal to what? QPSK. That means basis function is most important, and this basis function will be utilized by the QPSK receiver in order to identify. So this is what exactly called as QPSK transmitter. QPSK transmitter, what will happen? This is the information absolute. This is absolutely information. The binary pulses of this will become a polar equation, and this equation will absolutely multiplex. Phi 1 of 2 into is equal to what? Phi of 2. Okay, this is 2 equation will exactly will divide this according to even and odd. Okay, and this will be multiplied by the basis function, and exactly we'll get back to QPSK. Okay, right. So similarly, we have the coherent deduction. All I explained in last class. Okay, exactly here the coherent. Okay, exactly the right. That is exactly. This is coherent deduction of the QPSK is signals here exactly here. The what will have received signal is, let us say this received signal is received signal. Okay, exactly. The received signal is x of t. As I know, the signal will be absolutely will be multiplied with the bias function which are locally generated by the receiver, and it will be integrated absolutely with the what for a time period 0 to TB. Okay, exactly. In this case 0 to TB, 0 to t of this decision variable. Okay, look back here. This voltage. Okay, exactly. See, look back. What will happen? 0 to t, and this is the signal will come now. Whether this signal is one has to identify with the decision devices. Absolutely, this decision devices will compare with the threshold voltage 0. This is the voltage x1 of 2. This whatever the things comes here, it will check with the decision making threshold of 0, and add which will all together is multiplied and estimate this signal by multiplex the two things here and estimate the transmitted signal. Look back here, in QPSK 2 signals has to be generated. Whatever the receiver comes here, each receiver will go to different basis function. Okay, different basis function 5 and 2 and 5 2 and integrated over this, and the decision devices will check the information is equal to whatever x1 of t is equal to decision 0, x2 of t is equal to what exactly? Decision of 0. This will become, this will be multiplex and estimate of this. Okay, so next now let's go back. What is exactly the error probability of QPSK? The QPSK signal is equal to SI of t. Okay, XI of t, this QPSK. Now, what is the probability, error of probability of QPSK? That means even if you transmitted one signal, even if you transmitted signal 1, and the receiving information is 0, that means the probability of deducting the information by the receiver is whether it's correct or not, that is zero. We absolutely we call it as error probability of QPSK. Please mind it, what is exactly the error probability? Error probability of the receiver is detecting the information is wrong. That means whatever the information detected the wrong, it is different from the whatever the information we assigned from the transmitter. So what is exactly there? See, look back, we already QPSK. QPSK, this is signal energy is square root of E by 2 into cos of 2 pi CT into 2I minus 1 pi by 0 less than or equal to elsewhere. Expand this because cos of A plus B. Okay, exactly. When you expand by cos of A plus B, we'll get back to this equation. Okay, exactly. This equation. Okay, this is integral of 2 p by t into cos of 2, this minus pi by 4 into cos of 2 pi ct, integral of 2 by t into sine of 2I minus t. So you look back, this is the input, this is the exactly transmitted signal. But now when you come back to the receiving signal, so it acts for the AWG in theory, if the QPSK is transmitted in AWG in theory, and then what you call it as, then the output is given by x of t, si of t, omega. This is the output. For example, when the signal is transmitted from the input to the exactly local generator. Okay, exactly. The input is output is equal to whatever this is input, and the noise will be multiplied to the input, and output will get back. That is x of t is equal to si of t plus omega t, as we mentioned this. So you look back here, very important. The signal transmitted si of t in the channel will multiply basis function before transmitting, and hence the output signal of the QPSK is also a function. That is why in the QPSK we have mentioned it. The basically what we are finding, error of probability. What is exactly the error of probability? If the possibility of the error, possibility of the receiver detecting the information wrong, that is whatever the information received, it is different from the information what we are sent from the transmitters. Okay, exactly here. So look back, x of 1. Okay, exactly, x of 1 integral is x of 2 pi of 2. This is the, we know that means output has to be in the function of the basis function. Exactly. So output is equal to what exactly? X1 of x pi of t. See what is exactly x1 of pi of t. We know that what is x of t, it has to be energy, and it has to be what exactly? Cos of 254. And similarly, this is absolutely x of 1. See, this is for one path. That's a quadrature path. That is first signal. As I mentioned in the QPSK, what will happen? One signal, 2 bits will be generated. For a one signal, 2 bits. One bit for 1, another bit for 0 to identification. That is why the x1 is equal to this h value. Okay, 2I minus 4. So look back here, 2, this cos x of 1. So this, because look back, this is output with the input plus Gauss, as we mentioned, as because since you're using QPSK in AWG in channel, the white Gaussian noise in the noise path. X of 1 is equal to 0 to pi, x of t, pi of 1 into dt, integral of e, square root of e into off, because look back here, cos of pi by over, when I is equal to 0, okay, exactly, when I is equal to 0, will what will happen? Cos of is equal to pi by 4. When I is equal to 1, let us say, first equations are not, it cannot be 0. It will be equal to 1. 2 minus 1 into pi by 4. Exactly cos pi by 4 is equal to 1 by root 2. Look back here. X of 1 is the signal to transmit 1. X of 2 is equal to the signal which is received for 0. Okay, exactly. So for I is equal to 1, x of 2 pi 1 into omega, it is what you call noise signal. X of 1 integration of the, okay, exactly, x of 1 plus square root of e by t into plus output signal in the noise path of this. Okay, exactly. Look back here. Similarly, for quadrature signal, for a singling of the figures, look back, QPSK has a two phases. One is cos omega c minus sin omega z. This is for cos omega ct, you always send for signal 1, signal bit 1, and that is a signal 1 means exactly transmitting the bit 0, bit 1, when the cos s2 of t is equal to transmitting the bit zeros. Okay, exactly. So bit 0 x of 2 is equal to integral of e by 2 into this. Okay, exactly. So look back here. Basically, what we are finding, we are going to find what you call error probability. Deducting the bit is equal to 1. Deducting the bit 1 instead of what exactly. Deducting the bit is okay. Deducting the bit. Okay. Deducting the bit. Deducting the bit is wrong. Deducting the bit is exactly wrong. Is this okay? Deducting the bit is wrong. detecting the bit is wrong. Okay, so look back here. The QPSK has two phases is equal to exactly in phase path and exactly what second is what exactly the quadrature path. Okay, exactly. In phase path is equal to two phase in phase path and is equal to 1 BPSK. Q phase equal to 1 BPSK. So that means the probability of error of detecting the wrong information by a QPSK receiver is given by as for the BPSK is this. That means QPSK will consist of two BPSK by 2. That means exactly here, look back here. This is the what absolutely uh, P1 the in phase path is equal to okay, P is equal to Q into 2 E into EB divided by N2. QPSK receiver replacing 2B by 2 EB by B, since signal energy QPSK is equal to E by 2. See, this is for 1. So look back what exactly here the QPSK will have two phases. One is exactly in phase path and second is what you call quadrature. For in phase path, one of this is equal to probability and exactly quadrature is equal to what? P dash is equal to this. Okay, right? So this is for in phase. This is exactly for out phase. Okay, exactly. So look back here. But you look back here. The average, very important is the look back here. This therefore, from a working out QPSK, receiver with respect to in phase with account for one bit and remaining bit for another path, thus in phase quadrature for statistical independence. Look back for one symbol you assigned it, two signal will be generated. Each path, one path called as in phase, second path is a quadrature path. Each path is equal to have a probability of error as simple as same as that we want exactly in quadrature in BPSK. That means one path that in phases will have that was exactly in phases equal to probability error of finally detecting the wrong as of the BPSK and similarly that. So look back here exactly. So therefore the average probability of a correct decision resulting from the combined action of the two channel working together. Okay, look back here. So this is absolutely so P. This is the average probability of okay average probability is equal to 1 minus average probability is not happening. Okay, the average probability of detect happening 1 minus average probability of not happening. So for let us take for one path, this is in phase path is equal to probability are happening 1 minus average probability of not happening. PC is equal to 1 minus into square root. This is for happening for one path. So when you take this is equal to A minus B whole square, 1 minus 2 into this much. Okay, look back here. So the average probability of a symbol error for QPSK is exactly this is. Okay, exactly. This is for one path is like this. Look back. This is for one path. Okay, this is for one path. So for two paths, it has to be what? 1 minus P of this probability, and by ignoring the quadrature term as it will not contributing the symbol is this, right? So this is absolute. So look back here. That means first the equation. This is absolutely the error probability for QPSK is square root of E by T. Okay, like this is the transmitting energy per symbol E is equal to 2B. Okay, P is equal to 2Q by 2 by into square root of EB and not. Okay, okay, like so that means E is equal to 2B. E is equal to where is equal to transmitted signal energy. EB is equal to signal energy per bit, right? So 10 is equal to P is equal to 2Q square root of 2EB and that average probability error in terms of the QPSK. This is bit error. Bit error is equal to what? The probability by 2, because probability will indicate absolutely what you call it as what is the signal detected by the receiver is wrong, whether the correct information, whether the receiver information is correct or not. Okay, thus BER must be one of the average probability error in terms of the 2 bits of this is okay, because look back in bit error must be one of the average probability in terms of E by N because of the QPS, since 2 bits per symbol in there. For 1 bit it is this, because since it uses 2 bits, the bit rate has to be average probability by in terms of EB by naught is equal to 2. So BER of the QPS. Can look back here. See, look, we identify the probability error. First is equal to how we are going to look back here. Error probability equation, you will find it by imagining that QPSK will consist of two parts. One is exactly called as the in-phase path. Second is exactly was quadrature path. In-phase path, one path is equal to BPSK. Second path is equal to what exactly? Quadrature path. In-phase and quadrature path. Okay. In-phase path and is equal to what exactly? Quadrature path. In-phase path is equal to what is the probability error of this given by P is equal to 2k into e to the power. That means we have to take the two probability error of the in-phase and the quadrature path exactly. When you take the, we are able to derive this equation as I mentioned in the last pages. P is equal to 2k into e2 by et. See, look back, bit error rate, how many error, what a bit error rate is talks about, what frequency transmit of the bit. Here for a one signal, two bits are being transmitted exactly. Bit error rate of a QPSK, QP is equal to square root of 2b into to square root of 2b into naught. Okay, exactly, right? So this has been clearly explained. The power spectrum, as I told you, the power spectrum of this, let's go for the next topic is power spectrum QPSK. What is exactly the power spectrum of 2PSK? The power spectrum indicate the energy and magnitude of the QPSK signal here. So since look back here, the QPSK, we are going to use a one carrier wave, but not two waves, not two frequency signal. Please mind it. In frequency, very shortly we're going to take a two signal. Here we are going to take a two signal with the same frequency. We generate the two signals in a QPSK, one signal with a one phase with the same frequency and same amplitude for transmitting the two signal. Please mind it, in QPSK we are going to send two signal for one signal. That means for a one signal to be transmitted, that means 2 bits for one symbol to be transmitted exactly along the channel. Okay, exactly. That means we are going to use only one signal, that is whose frequency is W bar C is equal to this. The signal is exactly transmitted over normalized frequency. Exactly the signal is transmitted. So that means what exactly the signal is within this. What is the magnitude? That is the energy. That is the information absolutely within the carrier over, because please mention it. Please, we have mentioned it already. The information we are going to send, it will be exactly the production of what you call it within the production of, okay, within the signal generator. Okay, exactly. Right. So that means this is QPSK. This means okay. So this is absolute. The value of the power spectrum is absolutely given by this equation. Simple. Everything is very clear here. Therefore, QPSK here, since the possible value of M needed in next, let's go for what I call as M array PSK. Okay. So far we have finished what we call BPSK. So secondly, we have finished QPSK, then QPSK generation and deduction, probability error as we defined it exactly. This is absolute. M array PSK, okay. So M array PSK, look back here, the QPSK generated two signals. One is exactly in phase path, second is exactly what? Quadrature path signals. Okay, in phase path and quadrature path signals. Here the quadrature path signal will have the very important path, quadrature path, and this what I call in phase path will have a different phases. Okay, absolutely exactly with the different phases. Okay, exactly a different phases. Okay, exactly a different phases with that. That means it can take a different values. Quadrature is not only by 90 degree, it may take the phase of the, but one thing very true in the QPSK, it has to take two signals, one signal for one bit, another signal for another bit. Okay, for that, for example, we want to transmit the same symbol one, so we need to generate two bits. As I mentioned, what we call as the die bits, which I already talked about in the last classes. The die bits will be used generated for transmitting the message one. So message one is equal to what? Okay, exactly here the message. Okay, exactly the message. The message will be transmitted by 1 and 0 with this symbols. Okay, exactly. So this is the phases of the two signal has to be different as for the PSK. The phases will absolutely get different 5 by 4 into M. Okay, the 5 by 4 into M. The phases of the equation will be changed. because we mentioned it's quadrature. The quadrature is only for because of the two signal a difference by 90 degree. Okay, but difference by 90 degree. Not only that, you can change all the frequencies signals. As I mentioned it in QPSK, the phase can take even 2 5 by 4 different. Phase can take 2 3 3 by 4 or 5 by 4 here. The phase can take m values. That is exactly we call it as, okay, exactly we call it as what? Uh, this is exactly called M array PS case. M array PS case. Exactly here, M array PS case. Look back. That is M array PS case, the one signal which can take m possible value of the phases rather than taking only two only four what we have mentioned in QPSK 5 by 4, 3 by 4, 5 by 4 or 7 by 4 what we have mentioned it. So m possible value that is a phase difference with the two signal MPSK will take the possible values of the m possible values and hence it is called M array PSK. This is the generic form of the word. Another form of what is here exactly we call it as QPSK. M array PSK is the one. It will be same as a QPSK. In QPSK, we assume two signal in phase path and quadrature path. A difference, okay, exactly. The difference is equal to the quadrature path and quadrature path, okay. Quadrature path, and whether will we take the phase difference 5 by 4 and 3 by 4, 5 by 4 and 7 by forward. But instead of that, instead of the what we define in the quadrature path, the phase difference between the in-phase signal and quadrature path 5 by 4, 3 by 4. Here we are going to define the what exactly m possible values, m possible values. Okay, exactly m possible values. Okay, impossible values. That means it has instead of the free. Here, look back here. Exactly, this is the equation of the QPSK. This is exactly QPS. Instead of this 5 by 4, what we define the QPSK, we define 5 by 4, 3 by 4, 5 by 7 for this. This exactly equation will take over in terms of what exactly that phase value will be changed because we have mentioned it absolute at the very value that the phase difference the two values will take a m possible value which is mentioned here. Okay, exactly. So that means here the QPSK, because as I mentioned the M array PSK is the generic form of the QPSK. That means it also generated two signals. Okay, these two signals will be generated for identification of the symbol either the transmitter or the receiver. In the transmitter transmitting, in the receiver to detect. Okay, but the phase difference, what we define a QPSK is 5 by 4, 3 by 4, 7 by 5. Instead of that, other one m possible values. That is why that is exactly called as m per SK. So that means we modified the equation of the QPSK in terms of what exactly m possible values of the phases exactly square root of 2e by 2 plus into cos of 2 pi t into this. Here we introduce, look back, I am introducing is exactly here m is equal to positive, e is equal to, as you know already, energy of the signal, fc is equal to carrier of the exactly energy of this. So you look back here, what we are done, since m takes the different values, possible value in the QPSK, we define it already. We pi by 4, 7 by 4, 3 by 4 and all these things. Okay, exactly. But in the MRA PSK, we are defining the phase difference is called absolute, which between the what exactly 8 values. Okay, m1, m2, m3, m4, 5 like for a 16, for m16 point. That means m possibly 16 values. Okay, exactly we define m2, m3. Look back, very important. I hope you studied in your analog communication. AM array communication is a very important. So look back, 3 bits will be transmitted in a one pulse. For example, if you let us say for a what is for a momentary, I'm just telling about this. MRA communication in your communication point, you must have studied some little extent. Okay, if you're not, please understand that MRA communication is a one. In one pulses, we are going to transmit three bits. Okay, exactly a 3-bit. Okay, exactly 3-bit 0001 one pulses. Similarly, if we send 4 into 3, 12 bits will be done. I hope you got my point. By sending within a one pulse, you are going to send a 3-bit. That means rate of transmission of the bits are more. That is why that is a very important, especially in the MRA communication, digital communication. One single pulse, let us say a positive pulse, some bit duration TB. Within the TB, you are going to send 3 bits. Okay, if you send a 4 pulses across the channel, let us say AW channel, you are going to send 4 pulses, mean each pulse will occur 3 pulses, 3 bits. That means 4 into 3, 12 bits has been transferred. The 12 bits of information has been transferred. That is why the MRA communication, especially digital communication, it has played a very vital, important role, especially in the digital communication point of view. That is where you are using M values. Okay, exactly. So that means by taking it to by taking the phase different values, I can generate a multiple of signals. I can generate a multiple of transfer of the information. That is the way the importance of MPSK arrays. I hope you got. Why did you use M points? That is a one M array communication. So we use the PSK. MPSK is the absolute. Okay, MPSK is the absolute. Okay, MPSK is the absolute of the absolute value. Okay, absolute value of the absolute phase value of the two signals, which you, when you correlate along with the M array communication point of view, M array communication point of view is the one within a 1 pulse we are going to send 3-4 bits. That means rate of transmission of the bits are more. Please try to understand that. Within 1 positive pulse, I am sending 3 bits. If I send a 4 pulses, I can send a 12 pulse. That means rate of transmission of the bits are more. That is what exactly called M array. In this also here, so we are using M phase value. That means for a QPSK signal, we are introducing M value. In that M, if I keep on changing 1, 2, 3 phase values, what will happen in the last equation I just mentioned here? Look back here. Okay, exactly. This is the absolute, right? Okay, look back here. This is the M value. This is the where the phase equation. This is, I'm going to check. This is the absolute. This is the original equation of absolute. Instead of M, this original equation is just pi by 4. By removing pi by 4, I'm just introducing what? 2 pi by M. M takes the value of 1 and 2. Then number of signals will also be exactly generated. M1, M2, M3. Okay, M1. Okay, exactly. M1, M2, M3, M4. All these things absolutely generated. And look back here in this M1, M2, M3 as are here. So there is a absolute. Look back, this is a M1 plus EB. That is a message point which I already explained, the BPSK and also QPSK. How exactly that point is for a positive within the region plus B, for a minus, okay, minus, that is for a transmitting the signal with energy square root of EB with minus point of minus 8. Exactly. So M1, M2, M1, M2, M3, all simple point of it. This is exactly M8. Okay, exactly. So this is exactly make the decision boundary between that point of. Okay. So this is now how, what is exactly the probability error of the MRA PSK. Simple as you know, BPSK is simple as, but look back here. Very important here. This is okay. Look. Okay, exactly. This is the distance between the LCD and this is exactly the from the this is exactly from this signal space what you defined it. This is signal space for what you say that the D12 D18 is equal to square root of E into square root of E into E pi by distance between the two these things. Okay, exactly. This is absolutely here. Okay, exactly here. Right. This is the signal. Absolute dimension here. See, this is absolute. This is the message point of a different phase value. This is exactly distance mention point, and this is absolutely the distance between the two. Distance between that is exactly is given here. Okay, exactly D12 and D18. Okay, exactly here D12 and D10. Okay, exactly. So that means this is the equation of the signal space. Now, what is exactly the probability of error detecting at the MPSK? Probability of error detecting 2Q is equal to square root of 2 by n into multiply that, because look back in this signal space, probability error of detecting, look back one symbol, there is exactly the decision boundary. The decision boundary, it is on either side of the M1 and M2. This is absolutely the signals here. Okay, exactly this distance between the M1 to other difference in terms of the sine pi by m, we are multiplied to this aspect to this, we'll get back to the what exactly, but that is 2k 2i by into this is the exactly 2q 2e by n naught into psi by m. This is absolutely probability. How we got it? Please mind it. We multiply. This is the probability of error of the one message deducting the information is wrong, multiplied to the exact the distance between the two into square root of e into 2 pi by 2. It's q is equal to 2q 2 by into this. So this is absolutely, this is p is equal to 2q square root of 2e by n2 into sine pi by m. This is absolutely probability of simple error is this much. Power spectrum of this, okay, exactly the power spectrum is given by is this, okay, exactly this is mpsk. This is for m, because look back at mpsk is the one value, so this is absolutely gives the value for different values of m. Okay, so one is this has been clearly explained. So already I told you so many times what is that power spectral density and all the factors. This is the bit rate, just mugging the equation. There's nothing more than no derivation there. Probably this is bit rate of 2p or p into less 6, and this is exactly the frequencies. Okay, exactly. So this is now okay, then next class we are going to do MRA along with what exactly the frequency shifting frequency. Okay.